Okay, so we're going to finish up chapter 3 here finally, which is good to see. Now, one of the things we've been concerned with in chapter 3, we've been really concerned with displays of data. That's really kind of just been it for us. So what we've done was last time we talked about the 5-number summary. We talked about how do we take quartiles, things like that. And so this time we're going to finish all that up and we're going to show a really nice visual display. We're going to show something called the box plot, which is used quite a bit in these sorts of things. Very popular measure. Let me allow people into the Zoom room. So box plots, that's what we're going to be focusing on today. So last time we did the 5-number summary, and we said, okay, so the 5-number summary is going to be the minimum, the first quartile, the second quartile, which is also called the median. So remember, the median was another name for Q2. And then finally and then Q3, excuse me, and then finally the maximum. Here, let me get my iPad going. 1 second. Morning. So those are the basics behind all of this. Now, let's say you have this set of data, the number of fish caught in a tournament by 11 people. Find the 5-number summary. So what we're going to do is we are going to say, okay, you have 11 different people. One person only caught 2 fish. Maybe they started the tournament and had to leave. They had to leave after like a couple minutes or an hour or so. But then you had other people would catch 40, someone caught 43 fish exactly, someone caught 49 fish, 50 fish, and so on. So let's compute the 5-number summary. So what is the very first thing that we have to do here with this data? Exactly. He said rearrange it. We have to arrange it in order from least to greatest. Or at least that's going to be kind of the best thing to do. Pretty much you're required to do it, especially to find the median. Well, thankfully, the data has already been arranged for us from least to greatest. 2 different people caught 51 fish, so it looks like 51 is the mode here. No one else caught, or no other number appears more than once. So 51 is the mode, but we're not really concerned with the mode a whole lot. So let's see, we want Q1. We want the min, and there's a couple different ways you can display the 5-number summary. The min, sometimes called Q0, the median or Q2, the third quartile, and the maximum value. So once it's all in order, the min is easy. The min is just the smallest value. The max is also easy. The largest value. So putting things in order just makes total sense here. Now to find the median, you could do your little cross-out method, or you can kind of do a little bit more mature method and say, well, there's 11 data pieces, so it's gonna be 1, 2, 3, 4, 5. It's gotta be the 6th guy, the 6th one. Has to kind of be it. Because if it wasn't, or rather, the 6th one here then has 5 to the left of it and exactly 5 to the right of it. So it just kind of makes sense here to do the 6th data value is going to be our median. And now Q1 and Q3 are pretty straightforward to find. Remember, you divide the data into halves, and if you have an odd number of data values, you ignore the median. And you say, this is the first half, and then this is the second half. Exactly. Yep. You don't use the median in both the first and the bottom, the first and upper half. You ignore it and divide it around this. If you had an even number of data like we did last time, then you would just say that you would do just the first half and the second half data, and there wouldn't be any values you'd have to ignore per se. But here we're going to ignore the median. And we split the data into halves. Then we're going to say, oh, okay, well, we just need the median of the bottom half data. We need the median of the bottom half data. So, and that's going to be our Q1. So, clearly, just looking at these 5 ones, that's the very middle value. So 49 is going to be our first quartile, and then 60 is going to be our third quartile. So we got the 5-number summary. Now I'm going to take a picture of it so I remember, because here in just a moment, we're going to need to use it again. Now, there's a couple things you can do. You can identify the outliers. It's pretty obvious 2 is going to be an outlier because it's just extremely different from the other ones. But remember last time we introduced a method using fences, and that's going to allow us to find the outlier. So let's see if we can leave the 5-number summary up there. It's going to be ugly. So nope. Okay, so drawing a box plot. A box plot is going to be a visual representation of the 5-number summary. The box plot is sometimes also called a box and whisker plot. Box and whisker plot. So what you're going to do is you're going to have to do a couple things. The first thing you're going to have to do is determine the fences. Remember, the fences were what we used last time especially to find outliers. The first fence, the lower fence, is the first quartile minus 1.5 times 1.5 times the inner quartile range. And the upper fence is the third quartile plus 1.5 times the inner quartile range. The inner quartile range is the difference between the third and first quartiles. Then you need to draw a number line long enough to include the maximum and minimum values. You're going to put vertical lines over the first quartile, the median, and the third quartile. Then you enclose those vertical lines in a box. We'll see an example of this in just a moment. Then you can label the lower and upper fences. You can literally draw them like brackets that look like fences. You draw a line from the first quartile to the smallest data value that is not an outlier. So any outliers on here get a kind of a special recognition. We put asterisks for them, and we don't include them in the core of the plot. Any data values less than the lower fence or greater than the upper fence are outliers and are marked with an asterisk. So you can jot this down if you want, this policy here. Procedure for finding outliers. If you feel so inclined, I'll give you I'll give you a minute or two to write it out. It's, interesting. Not incredibly interesting, but it is something. course, if you're watching this on the YouTube later, you could just pause and write it out and skip ahead to where we get past this point. So again, calculate your fences, calculate your IQR, make a number line that's going to be long enough to include everything. So let's construct a box plot for this data, for the fish data. Now our numbers range from as low as 2 to as high as 63. So remind ourselves when it'll be obvious here in a moment, but we're going to go ahead and remind ourselves of the 5-number summary for this data. We said that the minimum was 2, the first quartile, Q1, was 49, the median was 51, the third quartile was 60, and the maximum was 63. So let's draw ourselves a nice healthy number line. Let's count by 5s. Something like this. There you go. 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100, and that's probably good. So 5, 10, and so on. We're counting by 5s. This comes up to 100. So the first thing we need to do is calculate the fences real quick. We'll do that as a side calculation. Of course, that means we need the IQR. It's the third quartile, which was 60, minus the first quartile, which was 49. So 11. So now we compute the fences. The lower fence is going to be the first quartile of 49 minus 1.5 times the IQR of 11. 1.5 times 11 is 16.5. 49 minus 16.5 is what, 32.5? So 32.5, maybe I'll label a few more points. And you can double check my math on that, but I think I'm correct. Here's 20, here's 25, here's 30, 40, 50, 60, 70, 80, I'm sorry, I guess this one was 90. I guess this was 90 down here. Oops. There we go. Okay, so we're going to put the lower fence. I'll put it in blue. It's 32.5, so it's about right here. So I'm going to make an actual fence looking thing. I'm going to make a bracket. So that's going to be our lower fence. And now our upper fence just needs a little bit of tweaking.
So the IQR is the Q3 minus Q1.
Exactly. Yep, the interquartile range. It is the range of the larger interquartile Q3 and the smaller interquartile Q1. And now the upper fence, we take Q3, which was 60, and we add 1.5 times the IQR. So now we do 60 plus 16.5, and we'll get 76.5. So we come over here, here's 75. So something like right about here. So what we're going to see is we used a really long number line, but there was a reason we used it, as you'll see in a moment. Now the next thing we're going to do is we're going to put the first and third quartile on there. So we said that the first quartile was 49. So 49 is about right here. I'm going to put a vertical bar above it. Then I'm going to go to the third quartile, which was 60. I'm going to put a vertical bar above it. Then I'm going to go to the median, which was 51. So this is going to be a very tight box and whisker plot. And now I'm going to create a box out of the first, third, and median. Just like that. And this is exactly how a box and whisker plot will look. Again, we had to use a very large number line because of outliers. The outlier ended up making us really need a scale because the outlier is going to be all the way the heck over here. Now what we're going to do, I'll go ahead and do it now. You can do it as you please. You can label your outliers with a star. Now it's pretty clear the lower fence was 32.5, the upper fence was 76.5. Everything falls within those fences except 2. So 2 is going to be the only outlier. So what you can do is you can put a star above 2 over here. Little star. Or you can use an asterisk, is usually the protocol. And so again, this outlier makes us use a much larger number line than we normally would want to. But that's okay. There's not much reason. Oh, I see what I made a mistake. 25. Oh, well. That's not going to be a huge difference at the end of the day. Now we're going to draw a line to the smallest non-outlier. 43 is the smallest value, which is not an outlier. So 43 is going to fall right about there. So normally you draw this line to the minimum value if the minimum value was not itself an outlier. But since it is an outlier, I draw it to the smallest thing that's not. Then I can draw a line to the largest non-outlier, but the maximum is not an outlier, so I can just draw it to it. 63 would fall around right there. Something. And so this is really the meat and potatoes of the box and whisker plot, right here. And because this outlier was not just tiny, it was way the heck over here. Way over there. That really messed up the scale of it. Imagine there hadn't been an outlier. If there had not been an outlier, let's see if we can zoom in. No, you can't. But if there had not been an outlier, we would be able to just blow this part up and just look at this part, zoom way in on it, and then the box and whisker plot would look a lot larger than it really was. But the outlier kind of screwed us up on that. That's why the usual protocol with outliers is to throw them out, although I think that's a bit premature, but we can at least discover them. We can at least figure out what they are. So, there was already one down here. Hold on. So box and whisker plots are fun. If you're curious about how the spread of data looks and how it would translate into a box and whisker plot. If you had data that was extremely skewed right, like this. This is very skewed right. It's not symmetric about the middle. You have data that's way the heck over here. What that's going to do is that's actually going to push the median down a little bit to be a little bit on the left here, and that's going to make the right-hand side whisker really, 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 really large. That's going to make this right-hand side whisker really large because like the maximum is pulling the data to the right. So your box and whisker plot, you can kind of see how it translates into this. The meat and potatoes of the data is about right here, which is why the box is also about right here. But then there's a very large maximum value, possibly an outlier, that pulls it way the heck up here. So skewed right means you have a really large right-tailed whisker, or right whisker. But a symmetric data set, your box and whisker plot is also going to look roughly symmetric. You have the whiskers are about the same size. The median is right about in the middle. It may not be perfect, so we're not always shooting for exact symmetry. Look, this bar on the far left is a little larger than this bar on the far right. So we don't have quite perfect symmetry, but we have something that kind of resembles symmetry. And so your box plot is also going to resemble symmetry by result. Finally, if you have skewed left, your left side whisker is going to be really large, and the meat and potato is going to be over here to the right. So that seems odd. Skewed left means that you have some really small values that are so small they kind of pull things over. Now the meat and potatoes is still to the right, but skewed left refers to how far it pulls things down to the left. So kind of interesting shape of distribution here. So it looks like just for a little bonus, we can look at an actual MyLabs Plus problem here. The data to the right represent the number of chocolate chips per cookie and a random sample of a name brand versus a store brand. So, great value versus, man, I don't even know what the name brand cookies are because I only buy store brand stuff because I'm a true blue American hero. And so you can look at the box and whisker plot comparisons, if you took the time to actually draw up the box and whisker plot. So this one's not horribly interesting, to be completely blunt. Okay, so let's talk about your next exam real quick, your exam 2. Exam 2 is going to be taking place next week. If you look at our schedule, it will be open on the 6th and the 7th of next week, if you remember such things. A few helpful tips for exam 2. Unfortunately, it doesn't work with Chromebooks the way we're going to be doing this. So if you have a Chromebook, you have a few options. Your best option, though, is probably just going to be to borrow maybe a friend's laptop or something like that. But remember, for exam 2 and exam 4, we're going to be taking it using the Respondus monitor system. And the way that works is basically you're going to have your webcam. It's going to connect to your webcam and it's going to record you while you take an exam. Now, if that sounds creepy or something to you, I promise you it's not creepy. It's literally only going to be me who looks at it. I don't sit and I watch the entire video of you. What I do is I go in and I make sure that you have the right things at the beginning. And what the system does is it flags it if it thinks you're doing something that could be construed as cheating. But it's not going to stop you in the middle of your exam. It's just going to flag it and let me go back and look at it and decide if you were cheating or not. So if you're not cheating, if you're clearly just using your calculator, you can use scratch paper, then you're going to be fine. You don't have to worry about it. I've literally never had someone cheat on one of these things. So what do you mean? Oh, okay. So yeah, what it does is it flags you if it can't detect your face, but flagging doesn't mean it's going to stop you. It flags you and then it tells me that you did that, and I can go, and if it's just clear you're looking down at your notes or your calculator, I'm going to say, okay, whatever. So yeah, it might flag you for that, but it's not the end of the world, I promise you. You could even technically, if you have an emergency, if you have to get up and walk out of the room or something, or if you have a child who runs in the room screaming, as children like to do, again, it'll flag it. I'll go review it. If you really are worried, just send me an email, say this is what happened. I'll go review the video and almost guarantee it's not going to be a big deal. Yes, the formula sheet for exam 2. Yes, so what you can see is that exam 2 has its own formula sheet. You can find the formula sheets for all the exams in the modules. Exam 1 did not have a formula sheet because it did not require a formula sheet. But exams 2 and on, including the final, will have a formula sheet. You will have to try and print the formula sheet. Again, though, you have we have more than a week now. So you should be able to maybe get access to a printer, have a friend print it for you. You can come to Weatherford College and use your printing in the library or something like that to print the exam 2 formula sheet. Good question. Kara, go ahead. You have a question for me? I will gladly answer.
Yes, sir.
And then we'll start chapter 4.
I did print that formula sheet out.
Sorry, Kara, I'm muted.
Oh.
No, you're muted, Kara.
Can you hear me?
Kara, can you type it out? I think because I'm connected to the projector here in the room, the audio is just not going to work, unfortunately. Sorry about that. So while she's typing out her question, let me think if there's anything else to say. So yeah, it won't work with Chromebooks, but it should work with just about anything else. The way it'll work is whenever you try to go take the exam, you're ready to rock and roll. You'll need a webcam, obviously. Pretty much every laptop built in the last 10 years will have one built in, so you can just use that one. But basically, can I use my index card I made with the formula? No, unfortunately, because that would be construed as notes. So literally the only notes you can walk in with is the formula sheet itself. But you can use the formula sheet. So that's kind of like a meet you in the middle. But no, technically it is a closed note exam, closed book exam. You can really only use the calculator, the formula sheet, and any scratch work, which it has to come in and it has to be blank papers that you're using when you walk into the exam. So that is the policy, unfortunately. So yeah, definitely closed note. But yeah, so what you'll do is when you're trying to take the exam the very first time, you click it, it's gonna prompt you to download something called the Lockdown browser, but it works very easy. You download it and you install it. And then the next time you go in to take the exam, next time you click it, it's gonna open that Lockdown browser. It's gonna automatically connect to your webcam. And for the most part, from everything I've seen, people have had no issues with it. It works like a charm. It really does. Exactly. Yeah, you have the 48-hour window. You can take it whenever the heck you want. I believe you have Right. No, you don't have to, you can take it whenever you want. We're not going to be meeting for class either on that day, on the 7th, which is the Wednesday. We won't be meeting for class. So good question. So yeah, again, it's pretty straightforward, I think. Most people don't have any technical issues with it. It's going to run exactly like you think. Only this time it's going to be taken in Canvas, so it's going to be a slightly different system. Yes, no class on the 7th because that's going to be the day that we are taking the exam, or one of the 2 days you have. So we won't be meeting on the 7th. Monday, we'll be doing a partial review on Monday. Basically, there's 2 sections of chapter 4 we got to cover before the exam starts. We'll start the first one here today. And then so what we're going to do Monday, October 5th, is whatever we don't get to from chapter 4, we're going to finish that up. And then I'd like to spend the rest of class reviewing. You're going to have an exam 2 review pop up. But I'm just kind of giving you an idea of what next week's going to look like with the exam. I will be sending out on Canvas an exam 2 announcement, and that will have all this information in writing for you. So that should be helpful. Just kind of wanted to give you a little preview. So good questions. Okay. So we just finished chapter 3. We're done with it, and we're happy to be done with it. And now we're going to get into chapter 4, which is going to concern something called regression. So let's talk about it. Let's dive in. So in this chapter, we're going to be dealing with paired data. That means X data paired with a Y data value. So that's going to be like points. It's going to be like points. Remember, if you have the point 3, 5, here, we'll write it out. Remember, you draw it or you write it as an ordered pair with parentheses 3, 5. The first value you see is the X coordinate. The second value you see is the Y coordinate. And remember 3, 5, so you'd start at the origin, you'd go 3 points to the right. Now we'd need a scale on here, but 5 points up, maybe something like that. Give or take, could be the point 3, 5. If you had -6, -3, starting from the origin, you'd go left 6 units because it's -6 is the X value. So 1, 2, 3, 4, 5, 6 maybe. And down 3 units, -3 is the Y value, so 1, 2, 3 units down. So maybe that would roughly be the point -6, -3. So there's all kinds of points you can graph. You know, you might have this point, all these quadrants. What we're going to see is that like a system of points is going to be called a scatter plot. Anytime you just basically have a bunch of points together on an XY coordinate plane on a graph, you're talking about something called a scatter plot, a 2-dimensional scatter plot, because you have 2 variables, X and Y. Now, a few other things, you might have a scatter plot where you start to see maybe a little bit of a pattern forming. It's not going to be a perfect pattern. Oops. I should probably just use this. It may not be a perfect pattern, but you start to see what looks like a pattern forming. It kind of looks like, for this scatter plot here, it kind of looks like a line generally that looks like that is starting to form. A line, and remember we put arrowheads on the line. The arrowheads aren't actually on the line, they're just a visual indicator to say that the line goes forever in this direction. And down here, the line goes forever in this direction as well. But again, the arrowheads aren't technically part of the line. They're just like, it's like us leaving notes for ourselves. And so that's pretty much going to be a lot of what chapter 4 is going to be concerned with. We're going to look at scatter plots, systems of multiple points kind of plotted together, and see if we can find any patterns forming out of that. And if we can find a pattern forming, we would like to figure out what linear equation, what equation of a line will do that. Will be the best line of best fit, we're going to call it. Get as close to all the points as possible. It's never going to be perfect. It's not going to be perfect, but as close as you can get. We're also going to look at evaluating how good of a line that was. How much does that line really benefit the data and look like it's supposed to be linear? But we're going to see that there's other ways that you can model things. And while we won't get into detail on them, we'll just see what that means for it being linear. So we could have a little bit of a review about slopes of lines. If you remember, a line generally has this form, y equals mx plus b. Some of your calculators will call m, they'll call it a instead of m. But m is going to be the slope of the line. The coordinate 0, comma b, always is 0 for the x coordinate. B, found from the equation, is the y coordinate. That is called the y-intercept. It's where your line crosses the y-axis, simply put. And so it turns out these are the two elements that are going to form a line. X and y are going to stay the variables x and y. You just literally write y and x when you write the equation. But m is going to actually be a number that tells you the slope of that line. B is going to also be a number that basically gives you the y-intercept. Now, if you recall, now again, this is supposed to be a very quick, scant review of lines, of linear equations and functions and stuff. Because a more detailed review, well, frankly, that's knowledge that you're supposed to come in armed with from your previous math courses. So a positively sloped line, I'll use green. Or no, you know what? It's almost Halloween, so I'm gonna use orange. A positively sloped line, as you move from left to right along the axis, now you remember you could say that there's arrowheads here. Now, drawing the arrowheads is kind of a pain in the butt, so I won't draw them, but just tell yourself that these lines actually go on forever and ever along the same pattern. As I go from left to right along the x-axis, which is going from smaller numbers to larger numbers, this thing is on the up and up. That's what it means to be positively sloped. In fact, when I say it has positive slope, I mean literally the slope of the line is a number which is greater than 0, which is a positive number. And you can have that as a positively sloped line because as you go from left to right, it's increasing. That, while very mild, is still a positively sloped line there. Because again, as it's going uphill as you go from left to right. Now, a negatively sloped line is one that is going to be going downwards as I go from left to right. It's going downhill. That's a negatively sloped line. This is a greatly negatively sloped line. But now that looks kind of confusing. So we'll just have one representative on each graph. A positively sloped line is generally going up as I go from left to right. A negatively sloped line is generally going down. But it can do it in all kinds of ways. It can be up here. Ooh. You can change the general slope without changing whether it's negative or positive. Stuff like that. So that would be a negatively sloped line. And when I say it has negative slope, I literally mean that the slope, m, is a number which is less than 0. Less than 0 is also a novel by Bret Easton Ellis. So that's just a kind of quick and dirty review of lines, of linear functions. They have this general form. A straight up and down line, a straight up and down line, a vertical line, is said to have undefined slope, if you recall. And what that means is you could kind of think of the slope as being infinite. We usually don't call it that. And that one does not fit this equation form. But the good news is you're very unlikely, we're not going to see that in this course. That's just not something practical, because that would mean something real funky is going on with the data, which is so funky, it's not ever going to be something you would deal
No
with.
horizontal.
A horizontal line is a little bit more likely. In fact, it's very likely, and that's a great question. A horizontal line, let me borrow from this graph real quick. A horizontal line, which is exactly what you think, it's a straight, just left and right line, flat line, that actually has a slope of 0. That has a slope which is exactly 0, which makes sense because it's not sloping at all. Slope, you think of how steep the hill is or slant of the hill. And here that has no slope at all. There's no slant to it. So a horizontal line would have a slope of 0. That's actually really interesting because what we're going to do is we're going to have these scatter plots here, and we're going to eventually run something called linear regression, which is going to give us the equation of the line of best fit for a scatter plot. And if you get a slope that's near 0, and there's actual statistical tests we will run, a very simple one to determine that, then that means that there's no linear relationship between your x values and your y values. So great question. So a horizontal slope is absolutely something that could come up. But for now, we'll deal with just positive, negative, and see what happens when you get horizontal slope. Good questions. So generally speaking, you're going to be pairing a response variable with an explanatory variable, sometimes called a predictor variable. And so what that means, so, imagine if you had a sample of 100 people. Imagine you have a sample of 100 people. Let's say they're middle-aged men, which I'm very soon approaching that group, but I'm not quite there yet, but I am soon approaching the group of middle-aged men. That means I'm going to go get a Corvette. I can't wait to get my Corvette. Well, you're a younger man, so maybe Corvettes are just cool, period, right? Well, I'm jealous because I don't have a Corvette. I drive a Toyota RAV4, which is safe. That is, yeah, yeah. That's a long-term goal. I like that. Yeah, I like my RAV4. But anyways, so imagine you had a sample of 100 middle-aged men, all of who are dealing with high blood pressure. So they're going to get into a new study. And in the study, what we're going to do is we're going to give them a dosage of a new drug that we hope will lower blood pressure. So what we're going to say is that in that particular example, X is not just going to give it to you. X is going to be maybe the dosage, perhaps in milligrams, of the drug, of the new wonder drug we're trying out, that each man is taking. Now, some men, you're going to have your control group, we'll call them, where they're actually going to be taking 0 milligrams of the drug. They might be taking a placebo. But then you might have some taking 10, you might have some taking 20 milligrams a day, 30, 40, because you want to see what's the right amount that someone should be taking. Is there too much you could be taking where you're just harming the body at that point? And then Y is going to be the blood pressure readings. And so X would be a predictor variable there. You're predicting Y, the blood pressure reading, based on how much of the drug you're giving a person. You're giving one of these middle-aged men who drive a Corvette, and yep. So you might have some of your sample data might just look something like this. It's going to be a bunch of coordinates because let's say you talk to the first guy. Let's say dad 1 gets 10 milligrams of the drug, has been taking 10 milligrams for a couple months now, and his average blood pressure reading for that first number comes out to 125. There you go. That is now a sample point. 10 is the amount of the drug he's receiving, 125. Now that doesn't tell you what his reading was before he was taking the drug. So you might compare it to that, but we're not doing that at the moment. The next dad is getting 30 milligrams of the drug, and his average blood pressure reading is 115. The next dad is in the control group, he's getting 0 milligrams, and maybe he's got an average reading of 123. So look, his blood pressure is lower than someone who's on the drug. But if generally speaking, if you see a trend where the more milligrams you take, the lower the blood pressure, you could perhaps argue that something's happening, or at least there's a correlation. Let's say the next guy is taking 30 milligrams and his reading is 110. The next guy is taking 20 milligrams and his reading is 112. So that's what your sample data is going to look like here. It can't just be a bunch of numbers. It's got to be a bunch of paired values, one of which tells you the dosage of the drug this person's taking. The next number tells you the blood pressure reading. But this whole coordinate here, this ordered pair, is just one sample value for one guy. Does that make sense? So ordered pairs and coordinates, things we've learned from previous math courses involving graphing, are definitely going to be in play here. So these are what some of your scatter diagrams are going to look like. Imagine just a bunch of points drawn on the graph. Something like that. We'll see more detailed examples here. It kind of looks like, like a giraffe neck. If you're bored and like to see patterns and things that don't actually happen. Also, if you're ever curious about something, there's a psychological phenomenon, and I believe this is how you spell it. You know what? Let me just make sure I'm spelling it correctly, because I find it interesting. There's my phone. It's called pareidolia. And it's a psychological phenomenon that has developed in humans. That's how you spell it. That allows us to see patterns even when there aren't patterns. So pareidolia. This actually explains a lot of really weird things that happen. And I can actually relate this to statistics. This actually explains a lot of weird things you happen. You know how when you were a kid, you'd go outside in the summer and you'd lay, or maybe not the summer in Texas, because it was a nuclear oven, but maybe in like the mid-fall when it was finally decent outside, and you'd go outside, you'd lay out on the grass, you'd probably get some stickers, you'd probably get bitten by ants, there'd probably be mosquitoes and wasps trying to get you. Also, every allergy in the book is here in Texas, so you're probably sneezing and sniffling. But anyways, you would go and it would be a nice, wonderful fall day. You'd go hang out in your backyard and you'd lay on the ground and you'd look up at the clouds, right? You'd look up at the clouds and you'd see shapes forming in the clouds. Kids today don't do that because they're too busy making TikToks. But maybe some of us, when we were a little younger, we'd go look at clouds and we'd say, oh, that looks like a car. And I don't have a lot of imagination. So that looks like Scooby-Doo. That looks like, I don't know, a swimming pool. You'd see those things in the clouds. Obviously, they're not actually there. And you might have you might have two people point to the same cloud and see something different. That's an example of pareidolia. That's an example where your mind creates a pattern around something that is not actually a pattern. It actually, if you've ever, you all play with Ouija boards, if you've ever played with a Ouija board, or maybe you think Ouija boards are evil or something like that. Well, regardless of your personal feelings on Ouija boards, I can tell you they were just invented in the early 1900s as a game. They're just a simple game. And actually, research has been done that says that our minds naturally move the little thing. I don't remember what they call it, but it's the thing that spells out the letters. Our minds move it where we want it to go because of this phenomenon called pareidolia. We want something to emerge out of nothing. And so that actually explains the Ouija board. So pareidolia is really interesting. It's going to be especially interesting in this particular example here, believe it or not, because let's say you do have your scatter plot kind of looks like this. Let's say that maybe it would look more like this. Along the x-axis here go the milligrams of the drug that are being taken. Along the y-axis, you can see the blood pressure of an individual. You see that it's dropping. You see as I increase x, y is decreasing. So what we think is, well, it looks like roughly this linear shape is forming. I can maybe write this line. Again, it's not perfect. We're not dealing with perfection here. We're dealing with general trends that we see. We see that that line has a negative slope. So what we would argue is that as one variable increases, as I increase the dosage of the drug, blood pressure goes down, it drops. But here's the problem. We could just be seeing a pattern that looks like it's happening that isn't real. There could be no causative connection between the two variables here. That is totally 100% possible. And so keep pareidolia in mind. We'll talk about it a little bit more as we look at some more examples. But yeah, so generally speaking, if you see this pattern forming, what we'll say is that there could be an explanatory relationship, possibly. We'll definitely say that it looks like a line is forming, so we'll call it linear. And it even looks like it's a positive relationship. This is positive because as one increases, the other increases with it. This is a negative relationship because as one increases, the other decreases. So it definitely looks like something's going on there, and it's very possible something is going on. I'm not trying to completely throw it out. Now here, it looks like there is some kind of relationship here. It does indeed look like some kind of relationship is forming between X and Y. It looks like a rainbow, or a better word for it is a parabola. A parabola is forming. The problem is that's not linear. You can't just draw a straight line and suddenly it explains that. So we would argue that while there's still a pattern forming, it looks actually like it would be a quadratic pattern and involve a parabola. So we are not going to say it's linear, and we actually can't model it with the tools we're going to be doing in this course. But it's just interesting. Here you also see a pattern forming. It looks like a spline, they sometimes call it. That actually, to me, looks like a third-degree polynomial, a cubic polynomial, whereas a linear equation is a first-degree polynomial. So it's still not linear. I can't just form a line out of that. I can try, but it doesn't quite look like it fits the pattern, at least not as well as these two did. I can try, but no cigar. So there's definitely a relationship here between X and Y, or appears to be, but it's not linear, so we can't exactly model it. And then here, it looks like there's no relationship forming. And you might say, well, isn't that like a horizontal line if you drew the line of best fit? Yeah. But a horizontal line is exactly, it has a slope of 0. Here's a hint. The slope of the line is going to tell us the relationship. How much does Y change for every change in X? That's what the slope of a line is going to tell us. If the slope's 0, then that means X has no bearing on Y. For every change in X, the change in Y could be anything. It's not guaranteed to happen. So we're going to say if it looks like a horizontal line is forming, I mean, look, imagine if I added even more points onto this scatter plot. Imagine I added some more that were just kind of all over the board. Nothing's really happening. Nothing interesting is forming out of that. It's just kind of like we randomly put dots all over the place and I don't see a pattern form. So if you have a horizontal line of best fit, a line of best fit with a slope of 0, nothing super interesting is happening. So let's call it for the day on that. We just started chapter 4. And so we'll meet again on Wednesday. We'll probably finish up that section and start the next section of chapter 4 as well. Definitely we're in calculator territory now because we're going to be computing the line of best fit, the slope and y-intercept, and we are going to need a calculator to do that because the formulas are just beyond what I think we need to do by hand. Okay, y'all have a great day. I already took attendance and keep it real. We'll see you Wednesday. Bye.